Hey, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent materials science graduate at the University of Ontario Institute of Technology, also known as Ontario Tech U. I also took my Bachelor's of Science in Chemistry at this institution as well. So today we're just going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or if you needed some tutoring, then check out the links in the description below. Okay, so I'm just going to get started on the set of questions. Okay, so question number 1. Which of the below molecules will have an odd-numbered molecular ion? Okay, so before I answer the question, I'm just going to give you a brief explanation as to what the nitrogen rule is. And basically, if the mass of the compound so we're looking at these different amine groups. If they're even, then there's an even number of nitrogens. Then and the opposite holds true as well. So if the mass of the amine is odd, then there are an odd number of nitrogens. Okay, so let's start answering the question now. Let's look at compound number A. You'll see that there's only one nitrogen present. So therefore this is odd. B has 2 nitrogens. So this one is even. And C I'm gonna draw it. So there's 1, 2, 3. This one is going to be even as well, since there are 4 nitrogens. D Okay, so this has 2. So this one is even as well. Okay, now I'm just going to draw out E. And this has 5 nitrogens. So therefore this one is an odd-numbered molecular ion. Then let's check the answer our junior tutor said. According to the nitrogen rule, the mass of amine is an odd number where an odd number of nitrogens is present. So only A and E are the odd-numbered molecular ions, and then B, C, and D are all even. So this solution is Correct. Now on to question number 2. Okay, so question 2 says, predict the major organic product of the following reaction scheme. Okay, so let's write down our reaction. This is question number 2. We have like a benzene ring, and then like a double bond at the end. And it reacts with mercuric acetate and methanol. And then there's an NaBH4, so sodium borohydride. Okay, so these reagents and this kind of reaction that we're going to do is called the oxymercuration and demercuration reaction. Okay, so I'm just going to draw out the mechanisms to show you what's going to happen. Okay, so basically the double bond here will attack our mercuric acetate, kicking off one of those groups. And then you're left the compound like this. Okay, so you can see that this carbon has lost its double bond. So now there's a positively charged carbon there. And basically what happens is one of the methanol groups come in. And tries to neutralize that positive charge. And then you get a compound that looks like that. So now the oxygen has a positive charge. And then what happens again is that another methanol comes in, deprotonates that, and then neutralizes that oxygen. To afford the next product. Okay, and we're almost done. The role of the sodium borohydride is that it reduces the carbon and mercury bond. And then our final product looks like this. Okay, so let's see what our junior tutor said. So this is a different molecule altogether. So there's going to be let me just rewrite this product so we can see it. Okay. So solution is incorrect. An OCH3 group is added. The double bond is reduced. Okay, so that's solution incorrect. Now we're on to question number 3. Classify the following radicals by sorting them into the appropriate bins. So you have primary, secondary, tertiary, and allylic. So I'm going to write all of those down and then give their definitions at the bottom. So for primary, the free radical carbon is bonded to 1 carbon, 2 hydrogens. Just gonna make like a chart. And then for secondary, the free radical carbon is bonded to, as you can guess, it's 2 carbons. And then the tertiary is bonded to 3 carbons. And then lastly for allylic, the free radical carbon is bonded to a double bonded carbon. Okay, so let's go over our different radicals that they gave us. So the first one is a primary radical. It's only bonded to 1 carbon. Well, it's bonded to 1 carbon and then 2 hydrogens. Then the second one is a secondary radical. Okay, so you'll see it's bonded to 2 carbons, 1 hydrogen. And then let's look at the third one. So the third one is also a secondary radical. It's only bonded to 2 carbons, 1 hydrogen. Then let's look at the fourth one is tertiary. So you can see it's bonded to 3 carbons, no hydrogens. Okay, let's look at the next one. Is also a tertiary. Only bonded to the 3 carbons. And then the sixth one. Yeah, the sixth one. Okay, that radical is this carbon is bonded to a double bonded carbon. So this is an example of the allylic. And then for the last one, looks the same as the other one, except there's no double bond. So this is an example of the primary radical. It's only bonded to 1 carbon and 2 hydrogens. So let's look at our answer here. So they have this one as tertiary. This isn't part of the original question, but yeah, it would be allylic. This is also not the question, but that would be primary. And then this one is secondary. This one is the tertiary. This one is the secondary, which I got as well. And then the other one is the primary. And the solution was pretty much correct. Even though it was missing some compounds, it's still pretty easy to kind of guess why it was correct. Okay, so now on to question number 4. Indicate the stereochemical configuration for the tetrahedral centers shown below. Okay, so I'm just gonna write down this molecule. Okay, so assigning R or S configuration. Okay, so these are the kind of steps that you would take. The first one is to assign priority. Basically, this is mainly based on molecular weight. And then if you have a least priority, this is going to be in the vertical position. And then you're just going to count the priority numbers. And see what direction the priority is going. So if it's clockwise, then it's R. And then if it's anti-clockwise, then it is S. Okay, so I'm gonna do it for the site 1 first. Then I'm just gonna number the priorities here. So for site 1, this carbonyl group has the first priority. And this carbon is the second priority. And then this carbon is third. And then our hydrogen is the last priority. So then if I were to write out just like a basic thing to kind of picture what it would look like, putting the lowest priority in the vertical position. And then once you count from like 1 to 4, you'll notice this goes in a clockwise direction. So therefore site 1 is R. Okay, so we're going to do the same thing for site 2. I'll use a different color. And then we're just going to number the priorities. So in this case, nitrogen is the first priority one. This larger carbon group is 2. And this little methyl group is 3. And again, the hydrogen has the lowest priority. So since the hydrogen is sticking up like that, I'm going to draw it up here instead. Oh, so this is 4. So 3 is here this time. 1 is down there. And then 2 is there. And then if we were to number 1, 2, 3, 4, it also goes, oops, in a clockwise direction. Kind of like that. So this is also R. Okay, so let's see the junior tutor's answer. Here the priority groups are NH2, ethyl, methyl, H. Counterclockwise configuration is R. So they got the same configuration. The reason they said that it goes in a counterclockwise manner is because it depends on where you put your least priority, like what position you put it in. So for example, if you put your least priority in the horizontal position, then it's like the opposite. So it just depends on what you're comfortable with. Like either way is correct as long as you are consistent. So this solution is still correct, since both the configurations are R. Okay, so on to question number 5. Add curved arrows to the reactants to indicate the movement of electrons in this reaction. And then I'm pretty sure this is, yeah, question 5. So this is fairly kind of easy. We have an amine group here. This is ammonia. And then we have hydrochloric acid. Oops. Let me just Cl. Okay, so in this case, our NH3 is the base. You can see it like that. And then the HCl is our acid. Do the movement of electrons. You'll see that this one will deprotonate the hydrogen chloride. And then that gives us our final product. So now there's a positive charge on the nitrogen. So the chlorine has an extra electron now, and it has a negative charge. Let's see the answer. Yep, so same thing. The lone pair attacks the hydrogen, kicks off the chlorine, and then you're left with that as your final product. So this solution is correct. So on to question number 6. Both H2O and H2SO3 minus are amphoteric. A. Write an equation to show how that hydrogen sulfide can act as an acid with the water acting as a base. And then part B is the opposite of that. Okay, so I'm going to write the definition of the Bronsted Lowry theory. And basically what this is that your acids are your proton donors. So protons are just your H+, and your base are proton acceptors. So the first one, we want the water acting as a base. So let's do part A. I'm just gonna write down the reaction. So since this one is the acid, it will act as a proton donor, and then the water will act as a proton acceptor. So since the water accepted a proton, it now becomes H3O+, and this is our conjugate acid. And then this lost a proton. Now has a 2- charge, and it is our conjugate base. And we're gonna do the exact same thing in part B, except switch around the roles. Let's write this down again. So this time, water acts as our acid. And this is our base. So after water donates one of its protons, it becomes a hydroxide ion. So it's just OH minus, aqueous. This is our conjugate base. Then that will accept a proton and be sulfuric acid. And it acts as our conjugate acid. Okay, so let's check out the answer. The hydrogen sulfite ion has lost a proton. The water molecule gained it, hence this was acting as yep, so they have the same reaction. They did the same thing for down here. H2SO3 and then OH minus. So this solution is correct. Okay, so now on to question number 7. So it looks long, but we'll go through it. The student is examining a bacterium under the microscope. So the E. coli bacterial cell has a mass of M equals 2 femtograms, and then they do the conversion to grams, and is swimming at a velocity of V equals 5 meters per second with an uncertainty in the velocity of 7%. E. coli bacterial cells are around 1 times 10 to the 6, I believe. Yeah. In length, I don't think that's important anyways. And then the student is supposed to observe the bacterium and make a drawing. However, the student, having just learned about the Heisenberg uncertainty principle in physics class, complains that she cannot make the drawing. She claims that the uncertainty of the bacterium's position is greater than the microscope's viewing field, and the bacterium is thus impossible to locate. What is the uncertainty of the position of the bacterium? Okay, so let's just write down everything that we know so far. We know the mass of the bacterium, 2.00 femtograms. But I'm just going to convert that to grams, like what they did as well. But for the equation that I'll be using, needs it to be in kilograms. Let's just convert that to kilograms. Okay, so this is our mass. They also give us the velocity, which is 5.00. I think it's supposed to be micrometers per second, but then I'm gonna convert that to meters per second. Yeah, every time there's like a weird symbol there, I assume it's like micro. And then we're looking for delta x in meters. Okay, so after we write down everything that's given, we know that the uncertainty in velocity is 7%. So from there, I'll make it delta E is equal to our velocity times 7%, so 0.07. So our uncertainty in velocity is now the 3.5 times 10 to the negative 7 meters per second. Okay, so next I'm going to write down the equation for the uncertainty in momentum. Basically, this is delta P, and delta P equal to mass times the uncertainty in velocity. So just gonna plug the values in. Then you get a final value of 7.0 times 10 to the negative 25, and the units are kilograms times meters over seconds. And lastly, for Heisenberg's uncertainty principle, it's the following equation right here, where it's delta x, which is what we're looking for, is equal to h over 4 pi times the uncertainty in momentum. So that's the delta p that we just calculated. So h is Planck's constant. So it's 6.63 times 10 to the negative 34. And its units is kilograms times meters squared over s. Then I'll just plug in everything else we know. Okay, so you can see that one of the meters cancels out, kilograms cancels out, and then the seconds cancels out as well, leaving delta x to have a final value of 7.54 times 10 to the negative 11 meters. Okay, so they also wrote down Heisenberg's uncertainty principle. They have the mass to kilograms, delta V, multiplying that by the 7%, and then plugging it into the final equation to get 7.5 times 10 to the negative 11. So this solution is correct. Okay, so on to question number 8. Draw curved arrows to show electron reorganization for the reaction step below. So this is similar to our other question, and it looks like there's two different parts. So let's write down the first reaction. So we have a double bond did cyclohexane. Cyclohexene. And then HBr. And then you'll see that the double bond is reduced, deprotonates the HBr. So its mechanism will look like this, where the double bond just tacks here. Electrons go there. And then our final products are the given. So that now has a positive charge. And then Br gained negative charge. Okay, so let's look at, okay, there's 3 parts to this. So let's look at part B. So this one wants us to draw the product that is formed and this reaction takes place. Let's draw the arrows in like they did. So the bromine acts as a leaving group. And then our final product looks like this. So the sulfur gained another methyl group. And you just have Br minus there. And then lastly, it's another draw out the mechanism question. Okay. So the lone pairs on the nitrogen pick up a proton here. And you get 4 hydrogens on your nitrogen now. This now has a positive charge. Then OH has a negative charge. Okay, so let's see our final junior tutor's answer. Doesn't look like they answered it. So I'll just write down. Okay, so solution is incorrect because there was no solution given. On to question number 9. Draw the major organic products of the following reaction. Okay, so this is sodium amide. And basically it is a strong base. So it's able to take this hydrogen away from the double bond to form the following. So I'll show the NH2 coming in. Let me just rewrite this. Okay, so yeah, this NH2 will come in, and that's how it gets deprotonated. So this now becomes just a negatively charged carbon. And then from there, once you add this brominated alkyl group, that negative charge can come in and attack right here, and that kicks off the bromine. And then you're left with this as your final product. Okay, so let's look at what our junior tutor said. So they have, looks like they just kind of grabbed that hydrogen out of there. Yeah, this doesn't look right. And the arrows are kind of confusing to see like what attacks what. and their final product is missing a couple carbons. Okay, so I'm just gonna say that the solution should have a new carbon-carbon bond between the carbon on the triple bond with the carbon that contained the bromine. The sodium amine deprotonates the triple bond, and then that negatively charged carbon attacks the bromine CH and then R group, and then the bromine is kicked off. Okay, so I think we have time for one more question. Question number 10. For the following dehydro halogenation E2 reaction, draw the major organic products including stereochemistry. Let's write down what's given here. So basically, since potassium hydroxide is a non-bulky base, it can come and deprotonate right here. That goes down to form a double bond, and then the chlorine is kicked off. You just make this double bond more noticeable. And then it looks like that. And if we were to name it, it would be E3-methyl pent-2-ene. Okay, so they have a trans alkene is formed, E3-methyl pent-2-ene. So this solution is correct. Okay, so those are all the questions for today's session. If you enjoyed today's Q&A and you'd like to be notified of when we do this next, then hit the subscribe button and notification bell below. And if you'd like to submit questions of your own, then check out the links in the description. And please remember to leave a like and comment if you enjoyed today's video, and also share it with all your friends and classmates. This has been Donna from OneClass, and I hope to see you soon. Bye!